This is a video about Dalton's law of partial pressures. Dalton's law of partial pressures states that the total pressure of a gas mixture is the sum of the partial pressures. And the equation for it is PT, which is total pressure, is equal to the pressure of one gas plus the pressure of a second gas plus the pressure of a third gas, etc. So I'll explain it in terms of drawing right now. Let's say you have a table, and I'll make it three-dimensional, and you have these gases that are hitting the table. We'll call the orange gas gas 1, so it's going to be moving around and hitting the top of the table and bouncing off it, of course, in different directions. And we'll call the blue gas gas 2. It's also going to be hitting the tabletop and bouncing off in different directions. And the brown gas we'll call gas 3, also hitting the tabletop. Well, let's say the orange gas is hitting, gas 1 is hitting the tabletop with 0.4 atmospheres of pressure. And gas 2, the blue gas, is hitting the tabletop with 0.3 atmospheres of pressure. And the brown gas is hitting the tabletop with 0.2 atmospheres of pressure. So they're all hitting the tabletop, but since there's more of the orange gas is putting more pressure and hitting it more often than the blue gas. The blue gas is hitting it the second most often, and the brown gas is hitting it the least often with the least amount of pressure. Well, the total amount of pressure on the tabletop is the sum of all three of these gases. So therefore, using this equation, you say the total pressure is going to be equal to the pressure of gas 1, which is 0.4 atmospheres, plus the pressure of gas 2, which is 0.3 atmospheres, plus the pressure of gas 3, which is 0.2 atmospheres. And when you add this all together, it comes out to be 0.9 atmospheres. This is going to be the total pressure that the tabletop is feeling, I guess, because of the three gases are all hitting it with a certain amount of pressure, but the total pressure on top of the tabletop because of these gases is 0.9 atmospheres. Now I'd like you to try this problem. Three of the primary components of air are carbon dioxide, nitrogen, and oxygen. In a sample containing a mixture of only these gases at exactly 1 atmosphere, the partial pressure of carbon dioxide gas is 0.285 torr, and the partial pressure of nitrogen gas is 593.525 torr. What is the partial pressure of oxygen? I'll give you guys a minute to think about this. Please stop the video now and then come back if you want to check your answer. So here's a container, and we will put all of these little blue dots I'm putting in it. We'll say our nitrogen gas, and there's a lot of nitrogen gas because the pressure for nitrogen gas is 593.525 torr. So they're going to be hitting the walls much more often than the carbon dioxide gas. The carbon dioxide gas I'm going to draw as black dots, and they're going to be hitting the walls less often, and because there's less of them, and this is going to be a pressure of 0.285 torr is the partial pressure of the the carbon dioxide gas hitting the sides of the container. So in order to solve this problem, you have to use Dalton's law of partial pressure, where the total pressure is equal to the partial pressure, which we have three gases. We have the partial pressure of carbon dioxide gas plus the partial pressure of nitrogen gas plus the partial pressure of oxygen gas. Well, we said we know that the partial pressure of the nitrogen gas is 593.525 torr. And we know that the partial pressure of the carbon dioxide gas is 0.285 torr. And we also know that the total pressure, it actually tells us, in the sample is 1 atmosphere, because it says in the problem, in a sample containing a mixture of only these gases at exactly 1 atmosphere. So it tells you the total pressure is going to be equal to 1 atmosphere. So right now you should see that we have a problem. We have our pressures in nitrogen and carbon dioxide in torr, the unit torr, and our total pressures in atmosphere. So we need to change either the torr unit to atmosphere or the atmosphere unit to torr. The easiest solution, I would think, is just to change the atmosphere unit to torr, because then you only have to convert one number to a different unit instead of both the torr units to a different unit. So let's change the atmosphere unit to torr. In order to change the atmospheres to torr, you have to first realize that the conversion rate is that 1 atmosphere is equal to 760 torr. So if something is equal to one another, I call this a truth, and you can change this, you can put this truth as a fraction and convert 1 atmosphere into torr using dimensional analysis, where what goes on the bottom is the unit that you're going to start with. So you're going to put 1 atm on the bottom, and on the top you're going to put 760 torr. And this one's actually really easy. 1 times 760 divided by 1. You could probably see it from the start that it was going to be 760 torr is the total pressure of the system. So you got the total pressure, you have the pressure of nitrogen gas, you have the pressure of carbon dioxide gas, and the only thing that you don't have is the pressure of the oxygen gas. So we need to solve for this variable now. On this page you can see it a little neater that the total pressure, 760 torr, is equal to the partial pressure of carbon dioxide, 0.285 torr, plus the partial pressure of nitrogen, 593.525 torr, plus the partial pressure of oxygen, which we don't know. That's what we're solving for. So now it's a matter of just doing the algebra. What I would do is I'd add these two things together first. When you add that together, it comes out to be 593.810 torr. And then don't forget to keep the partial pressure of oxygen on this side of the equation, and on the other side of the equation you still have 760 torr. The next step, in order to get the partial pressure of oxygen by itself, I would subtract 593.810 torr from each side of the equation. And after you do that, the partial pressure of oxygen is going to turn out to be 166.190 torr. And this is how you would find the partial pressure of a gas. And just to let you know, I did not take into consideration significant digits when I did this problem. Okay. I hope you learned a lot about Dalton's law of partial pressures.